My computer is showing 10 after. Um, so I
Yep, I think
will
that's
start.
a good time to start. So what I will do is, well, first, welcome everybody to Samir's Master's Defense. Um, I'm David Core, his official on-paper advisor, because his real advisor is Dr. Chen, who is now at Purdue. So I will turn it over to Diva to introduce Samir.
Right. Thank you everyone for joining. Thank you, David, for doing the official intro. Um, Paperwork and as well as everything virtual gets a lot more complicated, not just with the pandemic, but also with me having moved institutions. And fortunately, Samir has been resilient through both of those things, both the pandemic as well as the lab moving, and a lot of just years of doing his work, working really hard at his work, but just running into technical troubles or issues along the way. And despite the pandemic and everything, he's really pulled it together this last year to make it work. And it's weird to say because it has been literally a year, over a year now since I've seen Samir in person, although we have corresponded a lot online. And so hopefully everybody here can fully appreciate that. And we're all rooting for you, Samir. And since we are already starting late, let's, without any further ado, let's get you started.
Sounds good. Thank you so much for that introduction, Dr. Chan. And yeah, so I am here presenting my Master's Defense presentation for MRI-based strain mapping for cartilage repair assessment. So we focus here on the knee cartilage. So knee cartilage is a low-friction, load-bearing tissue that enables smooth joint articulation. Here is a diagram of knee articular cartilage shown as sagittal and coronal
Samir.
slices.
I don't know if it's not advancing for just me or you, but it sounds like you are not advancing on our screen slides. Not just me. Okay. It's still on the title slide.
It is? Okay.
For us as an audience.
Oh, okay. I switched it a few minutes ago, or it's been like 30 seconds now. Okay, give me a second.
Maybe you can just restart just in case it's an issue with that.
Does it show it now?
Yes.
Okay. Maybe there was a hotkey thing. Remember, I think we encountered this problem, WebEx hijacking hotkeys from other programs. Okay. I'll just very quickly restart. So, yeah, today I'll be presenting my defense presentation, which is MRI-based strain mapping for cartilage repair assessment. So we focus on knee articular cartilage, which is a low-friction, load-bearing tissue that enables smooth joint articulation. I've got a diagram here that shows knee articular cartilage as sagittal and coronal slices. The knee has the major bones, the femur and the tibia. Cartilage surrounds these bones on the femoral condyle and the tibial plateau, and is indicated in yellow here. This smooth tissue allows the joint to articulate smoothly through the entire gait, and also supports the body weight. However, a major problem with cartilage is that it lacks a direct blood supply and is not innervated, so when there is any kind of low damage, there is no pain associated with the damage, so people don't often know that they're actually being injured. These things result in this very poor self-repair ability that results in more and more damage over time. So according to the Osteoarthritis Research Society International grading schemes, we can see that starting with low-grade surface damage here, that progresses through the matrix over time, we can see that this damage cascades throughout the matrix until eventually the entire tissue is eroded away. This focal damage, which can start out at a single point in the joint, almost inevitably progresses to full-blown osteoarthritis, a chronic whole joint disorder. While the primary feature of osteoarthritis is cartilage loss, resulting in painful bone-on-bone contact, it also results in the formation of bone spurs, whole joint inflammation, and joint space narrowing. And this condition is associated with a very poor quality of life. So it's pretty clear to see why we'd want some kind of medical intervention to prevent that focal damage from ever getting to this point. But as with all things, there are additional challenges. So tissue engineering is trying to approach this problem, but a big first hurdle is the depth-dependent structure. So healthy articular cartilage has what we call a zonal structure. The matrix is depth dependent. Starting with the superficial zone up here, we have a high density of chondrocytes and a very tightly woven, cross-linked collagen ultrastructure. This runs parallel to the articular surface. The middle zone, the middle bulk of the tissue, has a lower density of cells and a very amorphous, randomly oriented collagen ultrastructure. However, the deep zone has vertically aligned collagen fibers, which support a lot of compressive load. Each of these three zones has unique mechanical properties and contributes to that zonal depth-dependent structure, which means that this complex structure is actually very difficult to recreate. So here we have an example of a cartilage study with an engineering implant and some host tissue. They're just examining stimulation versus non-stimulation on the repair interface. We can see that there's a clear interface between the engineered implant and the host tissue, which is enhanced with a stimulated repair. But this stimulation here, we can see that it visually improves. However, this depth-dependent structure here does not match that of the host tissue. And as repair efforts advance, how do we actually assess this repair interface? Like, how do we measure tissue integration? And it turns out that that repair assessment method, despite the advancements in tissue engineering, have not kept pace. So these repair assessments tend to be based on mechanical testing. So here we have an example of a simple compression test. A cartilage sample or piece of repair tissue is inserted between two steel platens in a bath and loaded. Depending on how much load is applied to deform the tissue a certain amount, we know that we can easily calculate the stiffness or the modulus of the tissue. But mechanical tests like these only examine bulk tissue properties, reducing information about that depth-dependent structure that we know has unique material properties to a single measurement for the entire tissue. And when measuring the repair interface, we actually see something similar. The repaired tissue here has some host cartilage with a repair material with some integration. A push-out, a rod, or some kind of indentation platform is used to push out the repair, and the amount of force taken to break that repair is measured. This is used to kind of measure, the stronger the interface, the more load it'll take to actually tear it apart. But again, that it reduces all that depth-dependent information, all that information about that interface, down to a single measurement. So while these mechanical assessments have improved, they don't pay attention to all of the key features necessary in cartilage repair. So in the field, it is well established that tissue should be fixed. Of course, we want a nice stable tissue that stays in place, and it should be morphologically continuous, meaning that it is smooth and matches the surrounding tissue. But when considering material property match, these studies only measure bulk properties, which effectively discards all we know about that depth-dependent structure. These tests also are destructive. They can only be performed once, and then the tissue has to be discarded. So if there's any kind of study that wants to look at repair improvements over time or changes in properties over time, these studies become very expensive because you have to keep making additional constructs and repair tissues for every time point you want to image. You can't reuse these samples. Not to mention for the interface, we see the same thing. These push-out tests reduce all the potential information about the interface down to a single point. So to address these issues, we need to visualize mechanical behavior to the full depth, non-invasively and non-destructively, so we can reuse the samples, which pushes us towards an imaging-based assessment. Fortunately, tissue engineering already recognizes the value of mechanics-based imaging through the use of strain mapping. In this example study here, the authors inserted some agarose as a simple repair tissue in a piece of cartilage. They found that when loaded with high-speed imaging, they were actually able to visualize this strain response depending on the nominal strain, and seeing that the shear strains along the interface are very clearly enhanced depending on what the increases in load. But while this approach is very, very good, it's not perfect, because it is still destructive and it alters boundary conditions. These setups are done with digital imaging correlation, which uses high-speed camera to actually visualize the movement of the tissue using fiduciary markers or known markers. The cartilage here is extracted, so it's still cut open and destroyed from a joint. It's put against a glass platform and imaged with the high-speed imaging, so you can clearly see the differences between the host and artificial cartilage. But, as I said, but you're still cutting the tissue out of the joint, you're still destroying it, and ultimately, by putting it on that glass platform, you're introducing observational bias because you're altering boundary conditions. So there is a need to visualize these through thickness mechanics non-destructively without altering boundary conditions. Currently, when looking at cartilage, MRI is actually one of the gold standards for cartilage assessment. It's non-invasive and non-destructive, and it's done in vivo all the time. It's based on established existing technology and has excellent soft tissue contrast. With MRI, there are also multiple imaging modalities available. You have your standard MRI, which can be used to visualize tissue morphology, quantitative MRI, which correlates with matrix composition, and diffusion tensor imaging, which has been shown to be sensitive to early cartilage damage. But what about imaging actual mechanics? So for that, we actually do have a technique that can use MRI-based strain mapping to visualize this behavior. It has been done in vivo, can be used to visualize large green Lagrange strains and pencil strains. It can also be used to measure cartilage and cartilage contact in an intact versus a defect model, to visualize the differences in the strain response when the tissue is damaged. But these assessments, while they do visualize through thickness mechanical behavior, have not been actually used to assess cartilage repair. So that brings us to the objective. The objective of this project is to assess the ability of MRI-based strain mapping in evaluating cartilage repair. So we know that cartilage repair should pay attention to a few key assessments: tissue viscoelasticity, depth dependence of its material properties, as well as looking at interface mechanics, mainly the interface strength. So based on paying attention to these key properties, we develop the following aims. Aim 1, whether MRI-based strain fields can be used to measure tissue viscoelasticity and depth-dependent changes in mechanical properties, and Aim 2, assessing the correlation between simulated MRI-based strain fields and material property match and interface strength. So let's start with the first one. Aim 1. We'll divide this into two sub-aims to address each tissue viscoelasticity and depth dependence independently. So we start by assessing the ability of multi-frame MRI acquisitions in fitting viscoelastic model constants, and then 2, looking at how strain distribution and mean strain can be used to detect depth-dependent mechanical property differences. So let's start with the first. We want to assess how well MRI acquisitions can look at this tissue viscoelasticity. We know that cartilage exhibits depth-dependent tissue viscoelasticity. That depth-dependent structure has unique properties in each zone. Viscoelastic mismatch can also introduce interface micromotion, and this kind of motion can inhibit tissue repair. So if we were able to visualize the viscoelastic parameters of the tissue to its full depth, it would actually be invaluable to assessing cartilage repair. So to do this, I start with a quasi-linear viscoelastic model. This model was chosen for a good fit of relaxation data, both in vitro and in silico. I have two exponential functions, which are modified by a stiffness constant, and use these exponential functions with time constants tau1 and tau2. The fitting was performed with the MATLAB curve fitting toolbox. We found in preliminary studies that we can image 4 frames during a loading plateau and still get a reasonable scan time. So we tried to fit this curve using 4 idealized points with injecting various amounts of scanner noise to simulate the MRI scanner over 1,000 iterations, a Monte Carlo simulation. Unfortunately, we find that the SNR to actually fit this model is much higher than is possible with current MRI technology. The SNR, the effective SNR, the noise injected, was varied logarithmically, so we find that to fit C, we require an SNR of 60 decibels, which in linear terms is an SNR of 1 million. To fit tau1 is even higher, 65 decibels, or 3.2 million, and tau2 is higher still, 10 million. This required signal-to-noise ratio is just not possible with MRI. And it makes sense. Traditional methods of parameter estimation use indentation testing, which uses sampling rates of 100 to 200 hertz, which end up with millions of data points that you can use to fit the curve. And while some research shows that MRI values do correlate with tissue viscoelasticity, this full-depth pixel-wise fitting will not be possible with MRI data. But at least that gives us an answer. We know that this won't be possible, so we can't use the multi-frame MRI to directly assess viscoelastic model constants. But at least gives us an answer so we can move on. We assess the ability of MRI-based strain distribution and mean strain in measuring depth-dependent mechanical property differences. So previous work has observed that there are depth-dependent changes in strain distribution there are certain strains at different parts of the depth of the tissue, which vary depending with material properties. But other work has also analyzed these spatial differences using mean strain. So when we do need to assess spatially dependent mechanical differences, because ultimately that's what we want to do, but should we be using the strain distribution or the mean strain? And some previous work actually gives us a head start in this department. So an earlier study has produced depth-dependent agarose phantoms using 2% or 4% agarose. They're either in a uniform constructs that are 6 millimeters tall, cylindrical, or they're produced in these layered manners with 2% on top or 4% on the bottom, and vice versa. The exact thicknesses of these layers has also been varied, so which creates depth-dependent structures. This 2% agarose is soft, while the 4% agarose is relatively stiff. So using the known layout of these phantoms, we know where the agarose concentrations don't match among the phantoms. So if we take their displacements and compute strains from their loading, can we actually use these strain maps to detect these differences? We know that the agarose concentration here doesn't match that here, so can we actually use a strain map to tell this difference? So using the uniform 2% phantom as an example, we have their exported displacement maps smoothed. We compute principal strains and maximum shear strain, and we divide it into a grid. We divide into a grid because ultimately, while we do want to look at depth-dependent differences row by row, we also notice that there are lateral differences in the strain maps as well, so we want to analyze those too. We analyze the strains per cell using these, and I'll show you this comparison as an example. We have the 4% uniform gel versus the 4% on top, 2% at the bottom, and 4122 sample. We know that the top layer matches, but the middle layer, this sort of midsection here, the middle third, is different, as is the bottom. These are 2%. So can we use the strain maps to tell this difference? This is the second principal strain of this comparison. We can see the uniform 4% tissue has a strong strain concentration here, but the layered construct has very diffuse strains, depressive strains, that are spread throughout the entire depth of the matrix. When actually comparing the statistics of the pixels in each of these cells, the strain values, we find that the mean strains are more sensitive to these differences. It picks up all the differences here that it should in the bottom. These are all statistically significant through the dark blue color, but it also picks up a few false positives in the top. And analyzing strain distribution, on the other hand, is more specific, but is not as sensitive, as it misses all of these cells at the bottom here. And we find that with an analysis of sensitivity and specificity as well. The mean strain is more sensitive, but less specific. This makes sense because the strain distribution ultimately adjusts for the mean value. It only looks at the shapes of the relative distributions to determine are these cells actually different, whereas the mean strains looks at mean values. And it turns out the means are the better differentiator of these cells, of these altered strains. So we find that this reduced specificity in the mean strain is actually acceptable because ultimately what we want to do is perform a correlation, and that gives us our answer. Can we assess strain distribution and mean strain in evaluating mechanical property differences? Yes, mean strain is more sensitive than strain distribution. So bringing us back to our aims, our overall aims, we finished aim 1, and now we can move on to aim 2, assessing the correlation between simulated MRI-based strain fields and material property match and interface strength. So to do this, we also divide this into two sub-aims, assessing the correlation of MRI-based strains of an inclusion and the surrounding tissue with its material stiffness match, and aim 2B, assessing the correlation of MRI-based strains of a repair interface with, again, material stiffness match, but also interface strength. So we can start with the first. So we know that we just saw in our phantoms that locally altered material properties changed the overall strain. In that phantom with the softer tissue on the bottom, the strains diffuse throughout the entire matrix more evenly, rather than stiff, uniform construct. So these altered strains propagate beyond that region of immediate altered material properties and change the strains in the bordering regions as well. So can we actually use the ratio of these locally altered strains and the bordering strains to make some kind of assessment of material property match? So to do this, I built an explant model with a rigid spherical indenter pressing in the center. This explant is cut in half, but is modeled as a rectangular cross-section of a cylinder with healthy tissue surrounding in much of the explant, but also a region of inclusion with altered material properties. This healthy tissue was modeled as a biphasic material, a solid neo-Hookean material with constant permeability, but the inclusion was modeled with altered stiffness and Poisson's ratio. it was ranged from 30% of the healthy tissue, which was very soft, to 150%, much stiffer. I applied the equivalent of 100 Newton load and used a non-symmetric steady-state solvent. The resulting displacements from the final time point were interpolated, injected with noise to simulate scanner noise, smoothed, and computed the principal strains. But if we actually want to look at the relative changes in the inclusion strains versus the bordering strains, we need to identify regions of interest, or ROIs, from each of the maps. So we computed these using the actual input geometry. You can see that each of the different representative cases here has a different amount of overall deformation and local deformations as well. And we find that we can actually compute these, what these areas are. This inner dotted line here is the zone of the inclusion, while this outer dotted line is what we consider the bordering tissue, a 5-pixel width zone. So this these regions of interest were used for the analysis. So now I'm going to show you the actual strain maps themselves. Starting with the 30% model here, so this is the model in which the inclusion is 30% of the stiffness of the rest of the tissue, so it's soft. We see that there's a concentration of high tensile strains in the inclusion and the border, a concentration of compressive strains, second principal strains, in the bottom of the inclusion, as well as a concentration of max shear strains in the inclusion as well. When we increase the stiffness ratio to 100%, so the inclusion matches that of the surrounding tissue, we find that these strain concentrations are reduced. The strains are reduced in the inclusion and the border. They are reduced in the inclusion itself, and now we see a nice smoothed topographical lines. And we also see a reduced concentration of shear strains. Now the shear strain is just evenly distributed through the middle of the tissue. And then finally, when we increase the stiffness ratio to 150%, we find that we see a return of these high tensile strains in the inclusion, a further reduction in compressive strains, and a further reduction still in shear strains, with a corresponding decrease in the surrounding tissue, but these strains are also moved around. So to actually evaluate how well these strains can look at material property match, we plot the mean ratio against the stiffness ratio and compute their correlation. So each of these plots can be used to compute what we consider the optimal model, where the mean ratio is approximately close to 1. The plot, in order to successfully evaluate the stiffness ratio, should yield an optimal model close to 100%, where we expect the material properties to match. We give this a little bit of leeway with a range of 80 to 120%, based on what a lot of other tissue engineering studies consider successful stiffness reproduction. So keeping in mind that the mean ratio is the mean strain of the inclusion over the mean strain of the border, and the stiffness ratio is the inclusion stiffness over the healthy tissue stiffness, we find that the first principal strain correlates very well with the stiffness ratio. The second principal strain correlates almost perfectly, and the maximum shear strain also correlates very well. As we increase the stiffness ratio, the ratio decreases. And when we're evaluating, we find that in this particular model, due to our eccentric location of the inclusion and our compressive loading, we find that the second principal strain is the best indicator of the actual stiffness ratio, but all three of these strains were very, very strongly correlated with the stiffness ratio. So that gives us an answer here. Yes, we can use MRI-based mean strain ratio to correlate with stiffness ratio and quantify the optimal range for these spatially dependent material property differences. So now we can move on to our second subject, assessing the correlation of MRI-based strains. Now, when we're looking at MRI-based strains, when we're looking at the repair interface, we know that material property differences can actually affect the interface as well as the interface itself. So repair efforts typically use adhesives or sometimes enzymatic treatment to bind the tissue together, while also trying to maximize the closeness of the two material properties. So with this, we find that the material property mismatch can also affect the interface strains. But can we use the interface strains alone to actually judge material property match as well as the interface strength? So we do something similar here. I built a patient-specific model using previously published data. This model here shows you 1/2 of the knee's cartilage, just the medial side. So here we have the femoral cartilage over the tibial cartilage and a very thin layer of bone modeled as a rigid body. I interpolate 9 slices through an 8mm full depth defect here, which you can see goes through the full depth of the tissue. And we can see that the sagittal slices here are the ones we'll be analyzing. We use slightly different model parameters, using an aggregate modulus and our confined compression, but varying the repair tissue, this blue tissue here, similarly. However, in this model, we also want to look at interface strength. So we varied the interface strength through maximum traction, the maximum stress it can take before it comes apart, from 0.001 megapascals, which is basically no integration, to 1,000 megapascals, which is virtually indestructible as far as cartilage is concerned. The final time points of these models were interpolated, injected with noise, again, to simulate acquisition from an MRI scanner, smooth, and we compute principal strains. So, when we're actually looking at these, we are looking at the individual slices along this model. So here is the model right here, shown as the fifth sagittal slice. This is the interpolation resulting. You see we have the repair tissue here, femoral tissue, and tibial tissue. And we compute 9 of these slices, or we interpolate 9 of these slices. However, while the analysis was performed with all 9 of these slices, only these 3 will be considered. So when we're looking at these 3 slices, we look at the actual defect models that have a discrete repair interface, indicated by this dotted white line, the boundary between the repair and native and healthy tissue. And we're also looking at an intact model, a model that doesn't have this defect created. In this model, obviously, there is no discrete repair interface, but we do our best estimate using the physiologically based model, and we approximate where the interface would be. So now I'm going to show you the seam strain maps using this exact view. So starting with the 30% model, we find that in the soft model, 30%, again, the inclusion stiffness is 30% that of the surrounding tissue, so it's very soft. We find there's a high concentration of tensile, compressive, and shear strains throughout the repair tissue and along the repair interface, varying in exact location. But as we increase the stiffness ratio, we find that these strain concentrations are reduced. They're not nearly as concentrated in the repair tissue, and we see a corresponding increase in the tibial tissue on the other side, as well as a decrease in the interface itself. In the 150% model, where the repair tissue is far stiffer than the surrounding healthy tissue, we find that the strains are further reduced, but we see a corresponding increase in the tibial strains, but with a further reduction in the repair interface. With our intact model, one that has no actual true repair interface, we find these strains are actually very similar to those of the 100% model. They're a little bit higher, and they don't propagate quite as much across the interface, but we do find that they behave actually very similarly. But again, we're not just looking at the stiffness ratio here. We also want to look at interface strength. So by varying the strength of this repair interface here, not just this one, but all of them, we are also going to look at how that affects the strains. And with very little integration, we see that we have a certain amount of strain concentration for the first and second principal strains and maximum shear strains. But as we increase the maximum traction, the interface strength, we don't see any differences. The strains are virtually identical as we increase the interface strength, and as we increase it even further, there's still absolutely no change. Compared to the intact model, these strains are a little bit higher and show similar topography, but it's overall not very different. So, plotting this data as before, plotting the mean strains versus the various parameters, we find that the first principal strain correlates very well with the stiffness ratio, and we see that we can also see the intact model is about similar to the 90% model. For the second principal strain, again, we observe a very strong correlation, and maximum shear strains, again, we observe a very strong correlation. But when we look at maximum traction, interface strength, we see no changes, just has no effect on the actual strain maps at all. The strains are actually very similar, but it didn't make a difference. But looking at stiffness ratio again, we evaluate it similar to what we did with the explant model. So here, instead of looking at a mean ratio of 1, we look at a mean strain where the repair model matches that of the intact model. So here, we find that the intact model matches at about 90%. We find that the second principal strain matches between 90 and 100%, closer to 100%. And for maximum shear strains, it matches at 90%. All very close to what we expect the close physiological model to be, with extremely strong correlations. In fact, almost flawless correlation. So we find that at least this gives us our answer. MRI-based interface strains very much can evaluate the stiffness ratio, but they cannot evaluate interface strength. So let's take this back to our overall project, the overall goals of our project. We found that tissue viscoelasticity just can't be measured by an MRI acquisition. There's just not enough signal there for us to make that assessment. But we can use the mean strain ratio to assess spatially dependent mechanical property differences. We can also look at interface mechanics, and we find that interface strains do actually tell us information about mechanical property match, but they don't tell us anything about the actual repair of the interface itself. So ultimately, overall, it means that MRI-based mean strains are sensitive to material property differences in cartilage repair scenarios. But this method, like any other, isn't perfect. We are still limited to in-plane 2D strains. We don't compute out-of-plane strains here, and much less 3D strains. There's information that might be excluded, especially in terms of out-of-plane motion as the tissue is pushed apart. We also exclude time-dependent information. Because the MRI scan requires the tissue to be at steady state, we also initiate a steady state analysis here, and we neglect viscoelasticity in our models, while also using only the final time point analysis. This is part of the reason that we didn't see a change with the interface strength. We also observed that there were strain changes beyond the immediate region of interest that we were analyzing. So, to be a complete assessment of the strain maps, the entire strain map should be considered, because it's information that we're losing. And finally, because of the manner of these regions of interest, this limits our process to in vitro or highly controlled in vivo work. So, to advance these methods and make them a little better and apply them to actual cartilage repair models, like physical models, we can first initiate a spatiotemporal analysis of these strain maps. We can improve our analysis to include all time steps and include viscoelasticity in the models, and we can use that to profile cartilage, we can use that to create a spatiotemporal profile of the cartilage strains in vitro. We can use a simple cartilage repair model in which repair tissue is removed and reinserted, or some kind of simple repair is initiated to get an idea of what good versus bad repair looks like. We can use this to compare typical treatments for 3D printed cartilage and tissue engineering to better optimize our cartilage constructs and decide what the most important features are. And using that optimized spatiotemporal profile, we can use that to assess the tissue repair of a live repair model over time. By being able to measure the progress of a single tissue repair sample over time, we can get a better idea of how much time is actually necessary for proper repair, while also mapping out what these spatiotemporal strains look like. So with that concludes the actual results of my study itself. Of course, I'd like to acknowledge a few people who were instrumental in their help. Dr. Chan and the whole lab have all been very, very helpful. Dr. Chan with her endless guidance, patience with my mistakes, and all her help with everything in the projects has been couldn't have done it without her. You just kind of leaving me speechless. Of course, Dr. Kaur and Dr. Wan have been helpful in their guidance, and actually Dr. Thompson as well has been very helpful with her mentorship and guidance for deciding where the project should go. Of course, I'd like to thank my family, my parents, my sister, for all their help and just their endless support through all these years. It's been a very, very long time. And at the end of the day, again, couldn't have done it without them. My friends, of course, especially those that went to grad school, have always been willing to listen, always willing to hang out, and spend the time needed just to maintain the connection and not losing sight of what's important. And of course, I'd like to thank Brittany, who remains an endless wellspring of gentleness, patience, and with whom I look forward to spending a very long time together. So, with that concludes my presentations. This is the brick wall of references, and of course, now I will take any questions. Thank you.
Thank you, Samir, for that wonderful presentation. I think you did an excellent job summing up what could be a very complicated set of experiments and distilling it down to a great story that people could follow. While you guys think of questions and Samir sort of gets some time to take a drink of water and relax from all that, I'll explain sort of the next steps for anybody not familiar with the process. Right now, we're going to open up questions and any comments from the audience. So public questions, Q&A for the candidate. And then we're actually going to kick almost everybody here off except for the committee so that the committee can ask our specific questions to Samir as well. And then after that, we'll come up with our decision and welcome, I think we can welcome everybody back, but I don't know if you want to, Samir. I leave that up to you, I guess, on what happens the back end.
Okay, sure.
So yeah, without any other distractions, if anybody has questions, please feel free to unmute if they can.
I
know
can
if you can.
change it so they can unmute themselves.
Okay. Might be the easiest way, or you can type them and I can convey them in the chat.
There are a lot of people here, so I was saying people can type and you can moderate like who asks what. I also have some Twitch viewers, so I'm paying attention to their chat if they have any questions. I'm going to work on letting people unmute themselves. Yep. Okay. And now attendees can unmute themselves. So if you want to, just click on your own name and you can unmute yourself and ask a question. Try to do it one at a time. Don't all talk at once. Dr. Wan, good to see you. I'm going to change Dr. Wan to a co-host. Jake, okay. I've got 2 private questions here. Don't worry, Jake, that's not a present question. That's not an ignorant question. Okay, so the question here is, in your region of interest analysis, you said you only considered slices 4 to 6 and threw out 1 to 3 and 7 through 9. What was the motivation for doing this? The motivation was to make my slides not a complete wall of color. They were actually all used in the analysis. I was just showing you those because those had the most interesting features and most quickly summed up the differences between all the slices. Yes, we did use all of the slices in the statistics and analysis. So from someone else, I have another question. Do the artificial tissues used for repair also have depth-dependent mechanical properties, or are they just homogeneous? Hannah, thank you for that. It's an excellent question. Yeah, they tend to be homogeneous. The tissue engineering field is moving towards recreating depth-dependent properties, and they are getting there, but they're not quite there just yet. A lot of studies have shown things like mechanical stimulation, natural gradients from nutrition, also just increase the depth dependency just by virtue of the tissue geometry. So they're working towards it, but aren't quite there just yet. Twitch, no one has asked anything. Yeah, any other questions? Again, you all can unmute yourselves now, so if you want to just talk, you can. Yes, I have a question from a Twitch viewer. I think they're typing. Again, no dumb questions here. Ask anything you'd like to. My favorite color is blue. I'm also just going to move my mic so I can pay attention to... Yes. So a Twitch viewer asked the question, you mentioned the 3 regions, but is there any value in analyzing the borders between these regions? So, kind of, yes. Those regions, some of them were border regions, and that's why we were analyzing them. The analysis, basically, I was trying to impart the fact that we should pay attention to the entire strain map, but the more we average over the entire strain map, the more we lose that spatially dependent information. So the regions of interest, those 3 regions, were kind of about a trade-off between excluding and including the information without over-averaging. Another question. In an ideal world, what experiments would you like to run to validate some of your models? That's a great question. Some of the experiments I'd like to do is, 1, doing this physically in cartilage. I'd like to run an experiment in which I have a cartilage explant with a spatial digestion or some spatially dependent altered material properties, and construct a spatiotemporal profile of the strain map to get an idea of how well the actual tissue degeneration matches that of the model. And for the tissue repair, for the patient-specific tissue repair, that one's probably a harder one, as I won't be likely having access to real-life joints of actual patients anytime soon. But at the end of the day, what we're ultimately looking to do is improve in vitro cartilage repair. So the answer is improving these cartilage repair models. Dr. Chan from the audience has said, do you envision any prospective evaluation of these findings? I'm not sure what you mean by prospective evaluation. What I envision is that tissue engineers will look at this, say that this information very clearly correlates with spatial dependent properties, so might take a second look at the MRI, at their university MRI scanner, which in many institutions often lies idle. How long does a Twitch viewer asked, how long does the process take? I'm sorry, what process? The process of the model and interpolation, or the actual tissue repair itself? For the former, it takes about 3 to 4 days. For the latter, we don't actually know. Most clinical follow-ups to tissue repair are in the 6-month to 2-year range, and they show within that time period there are a lot of improvements in patient-based outcomes, but after about 2 years, the repair actually begins to deteriorate, right? Which is why I have this whole project. We want to ultimately improve repair and repair assessment. Any other questions? Again, you all can unmute yourselves, I think. If you can't unmute yourself and would like to, let me know. I have the option selected, yeah.
Hey, Samir, just another quick question from me. This is Jake. Hey.
Yep.
So all of your modeling that you've done, that's based off of empirical MRI data, is that right?
No, the models generated here are finite element models, so they're based in tissue mechanics, and while they are simple models, they are meant to provide a base ground truth of what we know the tissue mechanics to be. From there, I treat them as though they were acquired from an MRI scanner. So we interpolate them into 2-dimensional discrete slices, exactly the way a scanner would, add some noise, the way a scanner would, and then from there treat them just the same process as I would using MRI data. So while, yes, they are finite element based, it is finite element based deformations, the point here is that we're meant to simulate what it's like to acquire the information from an MRI scanner.
I see. So would you be able to get your hands on some MRI data in order to actually perform these analysis yourself?
Yes, but not while I'm sitting at a desk during the pandemic.
Fair point.
But no, absolutely. So right before the pandemic, I was actively working on a spatial digestion model of cartilage samples, and we do have MRI data that I analyze spatially. That grid analysis that you saw, I submitted an abstract in which I analyzed the effects of cartilage catabolism on these strain maps using actual MRI data. A Twitch viewer. You mentioned it took roughly 3 days for the analysis process. Does that include the time it takes to generate the simulated MRI data? If so, how much time would the analysis take using actual MRI data? Oh, the analysis with actual MRI data is virtually instant, microseconds. The analysis here is just mean strains and looking at strain distribution. So that's what, a matrix of 400 points. Take the mean of that. Computers do that instantly. So that's no problem. What takes more time is establishing the setup for the right models, the right cartilage, that sort of thing. The actual scans themselves take a few hours, so that's the main time sink there. Okay.
Any last-minute burning questions from the audience?
Is this something I could foresee being done in a single clinical follow-up, for instance? I would say it depends on the improvements in MRI technology and the improvements in how these in vivo strains can be acquired, because it requires a fancy sort of rig to very securely hold the patient's leg and apply deformation. But I suppose hypothetically, yes, it could be done. Maybe after some custom fitting of the deformation device. But with that, I think that concludes much of the audience questions, and we will now move to the private session. Yes.
May I make a comment?
Oh,
Can you
yes,
hear
of course. Yep, I can. Took me a second to realize what that was. Yep.
So we used to have, I'm a cardiologist, in case somebody doesn't know. We used to have MRI strains, and we used to have a hard time calculating the MRI based strain because it was so time consuming. And now we have changed over to echo strains, and they are acquired very, very quickly, instantaneously, and takes literally a minute to acquire the strain in the heart and gives us invaluable information beyond which we could have ever expected. So, yes, down the line, I think the technology is evolving. It is possible. It's a comment.
Okay. Very good. Thank you. Ultimately, what I'm trying to show here is that, of course, strain mapping is valuable for tissue engineering, and that regardless of the actual method in which you acquire these tissue strains, looking at the mean strain and the mean strain ratio is what's giving you the information that you need to assess material property matches and such. And with that, I think we'll close the session. And sorry, Twitch viewers, you all get booted. And everyone else at WebEx.